Welcome to this webinar series as part of OpenRiskNet. Today we're going to talk about Nextflow and how we can use Nextflow for toxicogenomics inside the OpenRiskNet virtual infrastructure. It's going to be a little bit more of a technical talk than some of the other case studies that have previously been done. The idea here is we wanted to really showcase what we can do with OpenRiskNet and inside the virtual infrastructure around big data, and toxicogenomics is a great use case for doing that. So a little bit of background about OpenRiskNet. It's an EU-funded project, which is just entering, so it's coming up to the end of a 3-year period, which is in the end of November. And the idea is it's looking at risk assessment, so toxicology, and being able to determine the risks that are associated with materials or substances. And it's really an infrastructure project, so that means that we're really trying to develop sort of a computational platform, you could say, that is able to use all of these different tools and services which are provided by the people, by the other developers or external tools or partners themselves. So it's really driven by the case studies, and these are this is one example of the case studies in toxicogenomics and how we can integrate the existing tools into this approach. So this is part of a series, as I said before. There is this web page on the right-hand side there. You can see the OpenRiskNet events. If you click through to there, you can see the previous events which have been held, as well as the future events that are coming up. So a little bit briefly about what the OpenRiskNet virtual environment looks like, and this is sort of important to how we're going to deploy our toxicogenomics applications today. So you can think about as itself, it enables people to be able to, or partners to be able to put their applications on this and then be able to access the infrastructure. So be able to use the monitoring, the security, and continuous integration, and their applications sit on top of that in a way which will hopefully be able to be deployed anywhere. So the infrastructure itself sits on top of hardware, but this could be in cloud, on-premise, or even on the single computer yourself. So if we look at we have this production site here. If we click through onto this, we can see that we get a console for the RiskNet, and you can just sign in with any GitHub account here. You'll be able to log in and see your the console on the production site. So as I was saying before, the idea behind the infrastructure is that we can really deploy it anywhere. And in this figure here, you can imagine that the infrastructure, the environment can be deployed on a local computer or onto a cloud service provider, or even a local data center. And the main instructions for doing this can be found in this Wikipedia article here, which has been very well written and describing exactly how this can be deployed. And then if you click through to here, you'll find a description of exactly how it's done. So itself, it is built around a technology called OpenShift, and OpenShift is a container platform based on Kubernetes. And it provides an infrastructure, or a very basic infrastructure, for the execution of containers. And the focus here is really on services. And this works quite well for some services and for some applications. However, it doesn't solve all of the challenges related to orchestration or deployment of scientific workloads, particularly around parallelization and graph dependencies. So that's the things that we'll be looking at today, and specifically why toxicogenomics is unique in this aspect, or has some unique characteristics to it. So what is toxicogenomics? From a traditional risk assessment perspective, you often have read-across type analysis, where you're trying to determine if a molecule has a similar characteristics, whether maybe it has a similar structure or physicochemical properties, and you're able to determine if those characteristics are the same, whether it will have a similar effect. So toxicogenomics is different here in that our readout, what we're effectively measuring, is a biological response to a material or to a substance. And if you look at that figure, this is a figure which is describing toxicogenomics in the case of a nanoparticle. We can see all the different ways that the nanoparticle could enter into the cell. And then what we're able to measure here, in this case, is the gene expression. So the response from the cell will produce, will result in the expression of some genes. With those genes, we're able to determine what they are by mapping them to a genome. And then we're able to perform a differential expression where we're comparing, it could be, for example, control and treatment, and in determining which genes have been upregulated or downregulated. So the ultimate goal of that is to use that information, so to use that genetic information to understand the molecular mechanism and what's kind of occurring in the cell. So and by understanding that expression of the genes, so by understanding whether something goes up or down in response, we can determine if something is toxic and possibly look at the molecular biomarkers, so an expression pattern or a signal, which is made up of multiple genes together to predict toxicology or to predict toxicity specifically. And one thing that makes it different from traditional read across as well is that we also have this concept that the gene expression profile is made up of tens of thousands of data points. Each gene itself has an expression number associated with it. And all that together means that the data is very large. And with this large amount of data, we have different computational requirements that are observed in many of the other services provided as part of OpenRiskNet. So in toxicogenomics, the most typical analysis that we perform is called transcriptomics, where we sequence the RNA, and this is why it's called RNA-Seq. A typical analysis, you can go upwards of hundreds of gigabytes of RAM are required for indexing the genome. And then from the indexed genome, you quantify, which means you map the reads to the indexed genome to basically know how many reads from each sample are on which gene. And you're able to parallelize this process, at least at the sample level. So for every sample you have, you can parallelize it out. And that means that you're really only limited by the amount of CPUs that you have. And this is a situation where the cloud becomes very important, because you might just for a short time, maybe just for a few hours, you want a very, very large amount of cloud infrastructure so that you can just simply send out your jobs. They will run on the cloud, the results will come back to you, and it will really help you out as well. Also, there's increasingly situations where people want hardware acceleration, so using GPUs or special types of graphics cards. And but those may be hardware which you don't have within your own infrastructure. So you want to be able to submit those tasks out to specific cloud infrastructure that has that. I mean, in an ideal situation, you would have everything for free and it would be on your local computer, but this is obviously not the case. Our resources are usually limited, and we can use the cloud to enhance that. In terms of the storage as well, it's not insignificant. So a single sample of maybe 100 million reads, maybe around 30 gigabytes of data. And if you extrapolate that over thousands of samples, you can see that because the volume of data is so large, the location of the data becomes important. So it's not necessarily just the size of the data, but how close the data is to your external compute resources, if this is the way that you're going to do it. So if you now all of a sudden you need to compute in the cloud, how long will it take you to get that data and to location? So in this way, we need to use the data resources in a smart way. So if you were to consider that you had two infrastructure that are identical, one with a very large data set on it, and one with your application code, it becomes obvious that you think, okay, you just move your application to the infrastructure where the data is. And that's because there's a real cost associated with moving the big data. You can think of the costs of this would be in terms of network congestion, the time required to move big files, and simply the economic cost associated with transferring large amounts of data. In Amazon S3, which was the initial sort of cloud provider of storage, it costs around 10 cents per gigabyte to move. So if you had a 40 terabyte analysis, you'd be looking at around 8,000 euro in network charges and egress alone. So being able to move the computation to the data becomes very important. Two of these things that we wanted to sort of understand how this relates to toxicogenomics. So on the left-hand side here, you can see that this is the number of reads that are in the sequence read archive. Sequence read archive is the main repository for sequencing information in the world. This is an NCBI, but there is it's held in triplicate in United Kingdom and Japan as well. And you can see that now we're approaching 70 trillion sequences in there. So unlike a traditional, say maybe chemical database, which you could move around or you could install locally, this is the kind of thing that you're completely not able to do. And you need to have special tools for exploring the data. Another initiative which is started up and is becoming more common is where the cloud providers themselves are hosting the data at the location where the data will be, where the computation will be performed. So AWS at the moment has this concept of iGenomes, and they are reference genomes which are available in some locations of their cloud, in which case you can just use them directly without having to pay the cost of exporting the data out of the cloud. There's also some initiatives from the NCBI. I think one is called Strides, which is trying to really bring a lot of these public resources into the public cloud for people to be able to use in a way. Again, it kind of just all this together sort of highlights that the computation that we have and the computation that we're doing needs to be portable. And you can think about this portability in several ways. You have several options here. You could imagine that you could move the whole virtual infrastructure every time you wanted to do analysis. And with the OpenRiskNet environment, and it is somewhat possible, you could, if you wanted to, spin up a virtual instance of it on a cloud provider and then run your analysis there if that was required. But there's costs associated with doing that, with having the infrastructure up. Maybe there's time. Obviously, it would take time. I mean, there's a lot of energy required to doing that. But you could also imagine that you could just make your application portable. And that may work for some applications, but many applications it's quite difficult. You have to do low-level modifications to the code. Maybe you'd have to have it so that it can transfer data across a network. So it was being able to two instances of the same application can communicate with each other. These sorts of things become difficult. Also, you would have to modify the application for every different environment you wanted to work on. So the solution that seems to be that most people are working on and have sort of decided on a good way to do this portable computation is with scientific workflows. So scientific workflows, they're very much increasingly being used in scientific disciplines now. They're very useful in terms when you have jobs which are parallel or distributed. And they really allow a way for you to define the task. In this case, you have a specific set of steps which you are going through. You're able to split those tasks, distribute them across different nodes or across different infrastructure. And by doing so, you're able to really leverage the HPC resources that you have available and use them in an efficient way. You're also able to do this across different infrastructure, so you don't have to worry about whether your specific application works in one way, providing that you can put it into a workflow manager with a container. You get around lots of those problems. So some of the common workflow managers we have here is the Galaxy, which was probably one of the original ones used in bioinformatics, and it's it started life and mostly as a graphical user interface, kind of like a web console, and it's still very popular today. Some of the newer ones around we have SnapeMake, which is like Make, but more typically targeted for doing bioinformatics. And then we have Cromwell, which is from the Broad Institute, really focused around, started off with for running G80K, which is a variant pooling pipelines. And then finally Nextflow, which has been around since 2013, and which we actively developed in the lab here. So I'm going to just do a brief introduction now to Nextflow and why we how we can use it in OpenRiskNet, and how we decided to use it for the toxicogenomics workflows. So the toxicogenomics itself, if you can imagine that these applications, they're really doing on large data sets, we saw before, so the input data is very large. And they have this concept of embarrassing parallelization. So you can take each one of your samples, you can chop them up, and you can just run the same job in a distributed way. And sometimes you can do this with hundreds of thousands or even millions of jobs. And you're just limited by the number of CPUs you have. Also, lots of these genomics tools are a mashup of different languages and scripts and stuff you download from GitHub and something you wrote yourself in your PhD. And you need to kind of combine these things together and work in a portable way, but also be able to manage the dependencies. So being able to have all of the different libraries that a particular application depends on. And this makes for applications which are not exactly robust in a general sense. This is just a pipeline to show you, this is a genome annotation pipeline to just sort of describe how many steps are commonly used in here. And each one of these circles that you see here is a task. So there's basically a step in the pipeline, and you can see how the data flows through it. Now, this one here has 70 tasks and 55 external scripts and 39 software tools and libraries. So it's incredibly difficult to kind of manage that and to expect that you can naively just get that to work in any research environment, whether we could bring it into OpenRiskNet, or then even from within the OpenRiskNet, how would we ensure that we could run that externally and on a public cloud if required. And even if you can do that, so if people would spend the time, this is a paper that was looked at how long it would take to reproduce the result from a paper, and it's just to get the same result. When depending on how well detailed the paper is described, it's around 280 hours of work, and no one really wants to do that just to reproduce results. As part of the Nextflow paper, we showed here that even if you are able to replicate the analysis, depending on if you did the analysis on a Mac or on Linux, you actually end up with different genes annotated here, or different, in this case on number B, you see that the start and the stop sign, start and stop part of the annotated gene is actually a different location. And finally, around the transcript quantification, so this is very much applicable to toxicogenomics. You see that the numbers of genes that are called as differentially expressed was different between Mac and Linux. So there's massive problems in terms of doing this, and using a workflow manager and containers can help us solve this problem. So we're really trying to solve these issues around reproducibility, portability, to go in any environment, scalability, that it works in a distributed manner, usability, so that the user doesn't have to spend a lot of time to get a pipeline going anywhere, and traceability, so you know exactly what you've done and are able to track that. But ultimately, the goal of Nextflow is to have push-to-button pipelines which work everywhere. This is done through several sort of five main steps here. We have code itself, which can be written in any programming language you like. So whether you're into Python or R or Bash, or even more exotic languages. And these tasks themselves, which are written in code, are combined together. We're using this data flow programming model. And what that is able to do is, by combining those bits together, is as the data enters one of these, what we call processes, the task is automatically executed. So it's almost like the system is alive and waiting for the data, which means it's sort of data driven. The dependencies of each task is wrapped in a container, and then you're able to deploy them on these many different execution environments. Altogether, the integration with GitHub allows tracking of what's going on, and also being able to run pipelines from the Git hosting providers directly. A little bit about how it's able to do this. So we have what's called a custom domain specific language for the task composition. That data flow programming model effectively does the parallelization for you. So if I take a data set and I say, okay, split it or chunk it this way, each of those chunks becomes a task, and the distribution of the computation happens automatically. And each of those tasks is self-contained, and they cannot interfere with each other. They each run in their own directory or in their own container, and they're isolated. And this really helps with the portability, because then if you imagine you have a distributed system, you can't rely on any of the systems being able to communicate with each other. This is a typical task that you might do in bioinformatics, a bash command line script here, where we're taking a BWA, and we're just simply going to pipe it to SAM tools. In Nextflow, you simply would wrap the command line that you had before, and you just specify inputs and outputs. And this is one process itself. This is doing an alignment of the sample. And then we can join these two processes together, say if you had another step. And the way that Nextflow joins processes together is through these channels. So the output of the align sample process here becomes the input of the index sample process here. And this is the syntax that we use for doing so. As I said before, the data flow programming model is a reactive, like functional approach. So each of the processes is waiting for the data. And as soon as the conditions are met, the input says, the task is executed. And this is done through these asynchronous first in, first out queues. This means that the data itself is what determines what is run. It's very different from when you're trying to, for example, do a for loop and you want to say, this kind of operates in a slightly different manner. The parallelization itself, for every, if you're going to have a process here, the data inside the channel determines what is executed. And you can just write that itself. So maybe you're going to start with a single sample here. If you want to do parallelization, you just say every sample. And now this process will run as many times as there is data that goes into it. So as many FastQ files. FastQ is a read file containing sequencing data. So it splits like this. You can also do in sequencing, so in transcriptomic data, it's very common to have left and right reads. So you might have one sample and that has a left read and a right read. These are effectively just sequenced from the same side of the molecule, and you're trying to get them together, and then you determine the length of the sequencing read. In this case, you could have a gut sample, a liver sample, and by keeping these things together, you're able to keep the parallelization going. This is just basic examples of showing how this works. I'll go through this faster to move forward. That was the basics of Nextflow language, or what we call the domain-specific language. And what's more relevant to OpenRiskNet is the deployment. So if you just run Nextflow by itself, you could just run it on your laptop. You say Nextflow run, and it will just be running just using your operating system. You can choose to use containers or not, but it just runs in a simple manner. It also has these built-in executors for doing submission of jobs. So people have got like Slim, LSF, some grid engine, Univa grid engine. And in this case, Nextflow just has a shared file system, and when you submit the jobs to each job, just becomes, for example, a Slim job. So each task, and Nextflow handles the submission of the jobs and the determination of what's actually running. In some situations, you might need to pre-book or will create a cluster inside a cluster. There's clustering software inside Nextflow for being able to embed that. And increasingly, we see a lot of people taking up batch deployment. So in this case, it is AWS Batch. And AWS Batch is it's like an HPC in the cloud service. So you can submit individual jobs to AWS, and it tries to treat it like a traditional HPC job that you would be doing on your own cluster. And we'll show some examples of this a bit later on. Quite relevant for this use case, we have Kubernetes executors, and we have the special command for kuberun. And this is relevant because the OpenShift environment which we are using is based on Kubernetes, and the Kubernetes executor then is able to work well with OpenShift. So we are able to run Nextflow pipelines inside of OpenRiskNet using this kuberun commands. And what's happening here is the first Nextflow job becomes a pod, and then the subsequent tasks are subsequent pods which are able to communicate with each other via this persistent volume claim. The portability is essential. So while I just talked about the deployment scenarios, a Nextflow workflow should never, the actual contents of the workflow should never have to change for each of those environments, so that your application runs in all of them. So if I was running locally, I wouldn't have to put a config, but I would have the same workflow. If I was putting on Slim, I have the Slim executor. If I want to go run this now in the cloud, I just simply write AWS batch and determine my queue. The idea here is that you get this full portability, which is offered using the containers. And this is the main reason why this is possible, is because you keep the workflow logic separate from the configuration that's associated with the execution. And we're keeping these things very separate. You're able to run it away. Nextflow supported containers since 2014, which was quite early on, and they have a real big benefit over what people were previously doing with virtual machines. They're able to start up much faster. They can be relatively small, but compared to a virtual machine, they're immutable, and then we can kind of use them and build them and pass them over these software and services like Docker Hub that we were not able to do with virtual machines. So in Nextflow, each job itself is a task, and that becomes a container. And each job just becomes effectively like a Docker run command. And Nextflow handles the input and the output of the task, the mounting of the file system into the container. And then increasingly we're seeing people in HPC environments who want to use Singularity over Docker, over concerns around root usage. There's been a couple of other initiatives around Nextflow. So this is nf-core, which is for core facilities doing a lot of sequencing work, and they're trying to build best practice pipelines in. It's something you should definitely look into if you're looking into doing production level pipelines in Nextflow. And increasingly we're creating a sort of ecosystem around it so that you can have reporting on your jobs. You can determine resource usage depending on, in this case, you're looking at the CPU usage depending on the process, and tracking of the tasks so that you can look back and see what's happened. Have timelines, so you get a visualization of what task is taking so much time and how much resource it's using, and then a visualization of the whole workflow like we saw before. Okay. There's some syntax editors if you want to write pipelines of this, and this on Visual Code is quite good because now you have a remote access, so you can SSH in, for example, into the OpenRiskNet virtual infrastructure, and then write your code in there using the SSH connection. So very widely used. So it started to develop in 2013, and now it's in production since 2014, and becoming increasingly picked up by big pharma, small biotech companies, a lot of research institutes, and and it's really been focused to date on genomics, life sciences area, but slowly growing out into any sort of scientific data pipeline driven domain. So how do we get OpenRiskNet how do we get Nextflow to work on OpenRiskNet? Well, as I said before, the core technology is based on OpenShift. So the OpenRiskNet was based on OpenShift, and it's really a container platform based on Kubernetes. So to connect Nextflow into the reference infrastructure, into the environment, we simply created a project, which in Kubernetes you'd call a namespace. We just called that Nextflow. And within this project, what's happened is there's a cluster which is provisioned when Nextflow pipelines are executed. And these are dedicated nodes for executing Nextflow. They are labeled in Kubernetes language, and the default node selector is the Nextflow project. And the main thing to note here is the shared file system. So for the individual jobs to talk to each other, for the pods to effectively share the data, this means the input of one task, the output of one task becomes the input of the next task. We needed to enable this persistent volume claim, and by doing that, which connected up to an NFS storage, we're able to have it work. It's not an ideal situation, but it's kind of currently the best thing that we have while we're working on improving this. Okay, so you can there is a list on this on the OpenRiskNet repository if you wish to recreate this so that you can create your own Nextflow project inside any Kubernetes or inside any OpenShift infrastructure. There is a recipe which we have available. I'll just quickly show you that before. Actually, it's not this one here. This one here. So from the OpenRiskNet home, we then have this OpenShift. And inside here is a description of OpenShift. And inside the recipes here, we have all the different services that are available. And this is how we've set up the Nextflow cluster. So you can read a little bit about what we talked about here, how this works. And then you have the YAML file, which is describing, I think this one just describes the resources that are required for each of those things. So here we have persistent volume, how much storage you have, where the actual path is on the infrastructure. Cool. So with that, I would like to start. We can start to have a look how this works in practice on OpenRiskNet. So today, the stuff I will show is mostly using the command line tool. So just the command line from OpenRiskNet, but this is something that we're looking to improve in the future, and to have a kind of slightly more user-friendly experience through notebooks and the like. But it should still give you a good flavor of what's happening. So the first thing I'm going to do is just simply SSH into the environment. So I'm starting from fresh here on my computer. I'm just logging into a Bastion node, and then this OC command is actually going into the cluster itself. So now I'm going into OpenShift, and you can see that this is the list of the projects that we have on the reference environment for OpenRiskNet, and I'm automatically selected into the Nextflow project, but I could change the project if I wish to use some of the other projects there. Okay, so the first thing I'm going to run is just the hello world equivalent in Nextflow. And the way that this works is that normally with Nextflow, I would run a pipeline with Nextflow run, but because we're doing the Kubernetes setup here, we have this special command, which is kuberun. The only difference, sorry, another difference I should point out here is this requirement to specify this -v. And what this is the volume. So this is the persistent volume claim that we had before. We have to specify this so that the pipeline knows how to have a shared file system for the pods to be able to communicate. So the first thing that happens when we run this is that there's an initial pod, in this case, that just gets given a random name. And this pod here will then be the master pod, which will spawn the other pods off here. You can see that we're using the KDS executor here, and we have 4 processes which are run. Another thing to note is where this has come from. So I've said kubi run nextflow nextflow hello, and this is actually a GitHub repository. You can see that we have this hello world being printed, and Nextflow has this built-in support for running from repositories, and this is important to note so we can see exactly what's going on. So if I go, sorry, I thought we had this one open, Nextflow IO, and then I'm just going to say, in this case, it was hello. But you could have this as whatever you want. This is the basic hello world. We can see exactly what it's doing. It's rather simple. It's just saying, okay, take this channel, in this case it has 4 elements, and print hello world. And when we're doing that, we can see exactly what's happening there. We're getting this hello world. Okay, so that's the basics of how you can run a simple pipeline, and that does look rather trivial, but I think the important thing to note here is that if you can run hello world now, you're able to run any Nextflow pipeline, and that includes very large pipelines and that may be consisting of thousands of steps. The principles are the same. So that you can be guaranteed that you'll get the same execution. So now let's step it up a little bit and sorry, we consider what we've done there. Now let's do in terms of transcript toxicogenomics, let's do an RNA-Seq analysis. So in this case here, I'm just going to run the same command as I had before, so nextflow kubi run with the RNA-Seq, and I'm just going to mount the volume as well. And go here. So I'm sure this is dash A. And we see that again that the pod is submitted. And while this is running, we'll just take a few moments to grab. I'll go have a look at. We can have a look at the pipeline itself. Okay. So this is a RNA sequencing pipeline, which is doing what we do for transcriptomics. You can have a look at the basics of what's going on here. The main thing to note here is we have these different processes. So we have the index process, which is creating an index of our transcriptome. And this is outputting an index channel, which becomes the input of our quantification steps. And then we run some fast QC, which is a quality control step. And then finally, multi QC, which produces a report of what we had before. Okay. Okay. So with Nextflow, we are able to use this revision command. And because of the built-in support for GitHub, it recognizes that you can use revisions and you can use tags and you can even use commit numbers so that you run a specific version of a pipeline doing that. If we go back here, I can see that I'm here looking at master branch. I have several branches. I've got a KNS demo, a hybrid demo. I can use any of these in the same way that I could even use the commit number, so this number here. This is a really nice way to, if you think about your pipelines in a Git-centric way, then you can imagine that you treat your pipeline or you treat your workflow like an application in the same way that you commit code. So I will now run the master branch. And this is here we have the initial pod being submitted. So now that message there, it's saying that my local version I could update. So I could do Nextflow pull and pull that an updated version of the repository if I wanted. We can see here that we're using the Kubernetes executor. We can see the individual tasks being done. So we have one indexing task, and from that indexing task, we end up getting we have two samples in this case. So we have two FastQ samples, which means two FastQ processes, and two quantification steps. This pipeline looks really basic, I guess, but you could imagine that if you gave it 10,000 samples or 1,000 samples, it's going to run that many times, and you could be guaranteed. So we ran 6 processes in total, and the final one's just finishing now. Okay. In terms of the commands you can see, so you can run any of the OpenShift commands. You can see exactly what's been happening there. In this case here, I just want to say, okay, look at the pods that have been organized, and we can see that this is the previous pods that I've run in this environment, and you can find exactly where was the so we had this pod which was just run before, and then from there you might want to find out more information. But this is more just a tracing or just tracking to show you, just to demonstrate how Nextflow is launching the pods and is able to run. Okay, now let's get into to some cool stuff. So this previous example, I showed you that there was 6 tasks which got run, and each of them was running on the OpenShift environment, and it was all running locally. So you saw I SSH'd into the environment, and this is happening. I'm not sure exactly where the production server is. I think it's in Sweden now. But imagine now that I wish to step this analysis up. I mean, I'm just showing here sample data. But if I had a real analysis which required a very large amount of resources, particularly say the quantification step, and I wanted to run that in the cloud. There's a typo here. This should be AWS configure. And for this one, I'm going to show you how you can run this hybrid deployment with the quantification steps happening on AWS, and I'm going to have the rest of the steps happening on the Kubernetes environment. So we have several ways of configuring AWS. You can use this AWS configure, which is a command with AWS command line tools. You can put the AWS keys and your secret access into the Nextflow config, or you can use environmental variables. Okay. But the main thing to note here is that we're just going to run the same command, and now I'm just going to use a revision, a hybrid revision. So I will start that up, I think. And then I'll show you what's inside the hybrid revision that's actually enabling this to happen. Whilst this is starting up, we can go back to the main repository, and we can see that we are running hybrid now. And the only thing which is changing here is inside the config. So in our config that we have, we've simply added 2 lines. And what I'm saying is that, okay, if there's a process with a big task, put that on AWS batch. Otherwise, everything else will be just put through the Kubernetes executor. Okay. And now this is you can see that we have 2 different executors here. And the most important thing to see here is the staging of foreign file. So what that means is that we have our first step, which is executed, the index. And this staging of foreign file means that the file which is currently located in the on the OpenRiskNet drive has to be uploaded to the S3 bucket. So this is into the Amazon cloud. And Nextflow is handling this for us. And then once this is uploaded, we have to have the quantification steps, which will be occurring. And then when it's completed, the resulting output file, which is used for a downstream process, needs to be transferred back. And all this happens in a kind of transparent way. So to see what's happening, we should go into the Amazon console, and we can do that now and see what's happening in the background. So this is just my AWS console, and this is looking at batch. And you can see how you have these queues. This is very much similar to as you would have in an HPC system. And if I do a refresh on this, with any luck, I can see that I have two tasks here. So this was my two tasks which I just submitted. These are the quantification steps because the first indexing step is complete. And behind this, so what AWS Batch is doing is it's bidding firstly on spot instances. And these are instances where we make a price for us. And this is all configurable from Nextflow. So it's going onto the spot market. It's saying that I need this type of machine. And it's bidding up to, in this case, it's set as auto price, but it's bidding a maximum of 6 cents 66. And then when that order is fulfilled, if I go back to the instances here, we can see that that machine is running. Sorry, this is just really annoying. I should have disabled that. This is running here. And now when we go back to our command line, we can see that these two steps are still waiting to be complete. So we're transferring the files up, and this will just take a second. So what actually has to happen is the instance has to spin up on Amazon. And the most important thing here is that at the completion, so when our jobs are finished, when there is no more jobs in the queue, part of batch, those instances will automatically shut down. And that becomes very important in terms of your pricing. You want to be able to scale completely elastically. So if I have 10,000 samples, I want to have 10,000 jobs that are running and starting, and then as soon as I finish, I want to shut down. And the nice thing about batch is that you're able to put multiple jobs onto a single virtual machine. So if I have a virtual machine with 60 CPUs, if I only need a very small amount of resources, I can put 60 jobs onto that. Also, the way that the billing works in this case is that you have per second billing, which means that in this case, we just ran our virtual machine, and we'll get a readout from Nextflow here. You can see that the quantification steps have now finished in the cloud. And now we are transferring back the results into the OpenRiskNet virtual environment, which was here. This is the staging of the foreign file from the S3 bucket into OpenRiskNet, and then finally the processes multi-QC, which was requiring the first two quantification steps to be complete, is run. Okay. That is sort of showing you how we can do this hybrid and bursting with OpenRiskNet. And this is just a summary again of what was going on before. So for the tasks that we're using batch, we were transferring the data to the S3 bucket. Batch was creating a spot instance for us. We saw that. The whole job itself is a container, which is taken from the ECU entry, from the registry. And then the completion of the job, it comes back through the S3 bucket to Nextflow. And the user can just treat now the cloud as if it was a normal, as if it was just like a batch scheduler that they were using locally. We also have to think about the data localization thing we were discussing earlier. A recent thing which we have done as part of this project is to use this from SRA method, which we've been developing. And this allows you to, in this case, return a location of a file. In this case, we wanted to say for a particular sample ID, or you can actually do full text searches. So in the bottom example, I could say I want to find samples about liver toxicity in humans. And then by getting that, I'm able to retrieve the address. And from that address, I can then have steps which are required for that computation take place close to that data. This can be extended even further. If we look up the iGenomes project, this here I might be able to say, okay, which genome do I want? How do I want it? And I can find out, which region I would like to get it in, and then I'm able to do the computation at that location, like we were saying before. So that's a sum up of some of the work that we've been doing with regards to this project to date. The other things that we're really looking to improve around is the Jupyter Hub launcher. So as you saw, all of that stuff was really command line based, but having that stuff, we currently have a Jupyter notebook for Nextflow, but the problem is that when you saw the project namespace, that currently lives under Nextflow or Jupyter Hub, and the way that we're doing this execution in a distributed way, we need Jupyter Hub to be able to launch pods, which is a notebook or a Nextflow job or an Nextflow pod from within the same namespace. And we've got some ideas around how we can do that, and that will be a big improvement so that I can basically have what we had before, but in a more narrative-driven manner. We also want to consolidate some of the work that we've been doing in toxicogenomics into the case study, really into this is kind of related into the repository in a centralized way, so that it's a very clear story that connects the technological stuff we've shown here with a real use case, and then expand that use case out to include other data sets, which is something that we'll be working on over the next few months and continuing that. Also, I'd like to note there will be a report which is coming out very soon, which discusses some of these ideas and some of the things which we really considered to make this work in terms of OpenRiskNet. That report will be out hopefully very soon. You'll be able to find that on the website. And finally, I'd like to acknowledge all the people who have been involved in OpenRiskNet. You see there we have 12 partners from all over Europe, and it's a very collaborative process to date. And I'm sure that these last 6 months will be very fruitful for everyone involved. And with that, I just remind you of the final events that we have going. I'll click through to there, and then you can see some of the ones that we have coming up. In terms of the webinars, I think in 2 weeks' time. Feel for that. So on the 11th of June, 24th of June, and 15th of July, there's more webinars related to that. So I'm not sure if I can see if there's any questions, or if you have any questions, feel free to chat away. Otherwise, thank you very much for your time. It's a real pleasure to talk about some of this work. It's very exciting stuff. If you want to get in touch with myself or anyone from OpenRiskNet, then you can be able to find my contacts via OpenRiskNet website or Nextflow or on Twitter. Thank you.